Okay, so here is John's theorem, and last time we saw the proof of implication 2 to 1. So in the proof, we saw 2 implies 1. This was proven. Now comes the other part. So we will look at the proof of 1 implies 2, and this is from John's original paper, but the exposition here mainly follows the lecture notes of Keith Ball and Thomas Hickox, uh, and it was also given in Gruber's original paper. All these references you can find uh, in the lecture notes that I prepared. And so let's start. Okay, the main idea for proving 1 to 2. So what basically this says is that if the unit ball is the maximum volume ellipsoid of the convex body K, then we must be able to find a set of contact points and corresponding non-negative masses on these contact points such that these two conditions hold. And last time we saw that the first condition for a symmetric convex body is trivial. That's not giving you any new information. So we will focus on the second condition. And yeah, just for the sake of exposition, I'll in this video just present the proof for the symmetric convex body. But the non-symmetric case in full generality, you can find it in the lecture notes. I mean, the arguments are roughly similar, but I mean, you require a bit more algebraic manipulations and a little more uh, carefulness. So yeah, let's start. So the idea is that so we need to show that such basically let me write what we need to show. We need to show this happens, right? CI transpose I equals to 1 to m equals to in, and we can write it actually divided by n on both sides and call so note that earlier we saw that summation I equals to 1 to m ci equals to n, right? So this implies I equals to 1 to m ci by n equals to 1. So in some sense these ci's are actually, so ci by n is, and ci's are non-negative. So ci by n is, and so ci by n, sum of the ci by n is equals to 1. That means each ci by n is less than equals to 1. So specifically, we have something like ci by n belongs to 0, comma 1. And all these ci's sum up to 1. So you can think that these quantities are actually sort of giving you a convex combination in some sense, right? So I mean, and by renaming this Ci by n as Ci itself, we can basically claim that it's enough to show that such a thing holds, where Ci's are between 0 and 1, right? So the idea is to show that, like if you take these matrices, UI transpose, and you can think of them as a very long vector, right? So UI transpose is a n cross n matrix. And if I unwrap this matrix in the sense that, so this matrix has a first row, I write the first row here, the second row, I write the second row here, third row, like this, I'll get a long vector which will have n square entries, right? And this long vector, if I think about it, then this is saying that the convex combination of such long vectors generated by this UI transpose things, matrices, the convex combination, or rather the convex hull should contain this quantity in by n. So basically, if I can show that, if let me call this uh, set as convex hull of, okay, I did this this way. So C is our convex hull of the set U transpose, where U belongs to intersection of the boundary of K and the boundary of the ball. Right? These are the contact points, and C is the convex hull of these contact points. And by convex hull here we mean that you think of this UU transpose as like a long vector and take a convex hull of those vectors, right? So we need to show that In by n is in the convex hull, and that is sufficient, right? Because if it's in the convex hull, then we know that there exists these CIs between 0 and 1 such that you take a summation on this UU transpose UI transpose times CI, you get and sum them up, you get this quantity. So we will basically show that this happens. And as for general proof techniques, we'll start with the contract. We'll start with an assumption that suppose this does not happen, right? Then we'll end up showing some contradiction. Suppose In does not belongs to C. Now, what is the goal of the contradiction? The goal should be to show that indeed I will be able to find some ellipsoid which has a larger volume than Bn, because this is the only thing that is given to me. So I need to be able to construct some other ellipsoid of a bigger volume that will be contained in K, and that will suffice, right? That will conclude the proof that this In by n has to belong to this convex hull. So we will work towards that. So since we have assumed that this does not happen, so now we can invoke the separating hyperplane theorem. So separating hyperplane theorem says that if you have two convex sets that are non-overlapping, that are disjoint, then you can find a hyperplane that separates them. Separates in the sense that the one of these sets lie on one side and the other set lies on the other side of this hyperplane. So in this case, one convex set is the trivial convex set, which is a point, and the other convex set is the convex hull C. Right? So we will invoke separating hyperplane between these two sets, and so we will get is there exists H belongs to Rn cross n, right? And alpha belongs to R such that H of UU transpose is strictly greater than alpha, strictly greater than H of In by. So note that we are writing in this inner product form, and we earlier showed that this inner product form is same as basically writing them as long vectors and taking that inner product. This is just for the ease of representation that we will adopt this notation. Further note that the inequalities are strict because this In is just a like, so the inequalities become like loose when we have something like one of the bodies kind of touch the other body. In those cases, like you will have a hyperplane that separates them but does not do so strictly. But in this case, the separation is strict. So here we have some set like this and some point like this, right? So this there's like a hyperplane that has there's some gap between this and this. So these are non-zero gaps, and like intuitively that suffices to say that these inequalities are strict. So with this, now we can do some more argument to say that one H can be taken to be symmetric without loss of generality. And why is that the case? Because note that on the left hand side you have uh, H inner product U transpose. This is for all U belongs to. So basically on the left hand side, if you look at the elements of the convex hull right here, so these are symmetric matrices, and a convex combination of a finite number of symmetric matrices will also be symmetric. So here in the generality, what you will have instead of UU transpose is some matrix M which belongs to the convex hull C, and that matrix M will actually be a symmetric matrix. And on this side also you have a symmetric matrix. So basically, if you take H to be symmetric, nothing really changes. I mean, for more formally, you can say that, okay, this H comma M is symmetric. So this is nothing but I equals to 1 to n, j equals to 1 to n, H of ij times M of ij, right? And if M is symmetric, so you can write this as summation. Now we can collect the terms together and write this as H of ij plus H of ji by 2 times M of ij. This does not really change the thing because M of ij equals to M of j of I. So we can write this. So what basically this means that this is same as H plus H transpose by 2. And H plus H transpose by 2 is actually a symmetric matrix. So we can assume here on that H is symmetric, right? And the second thing to note here is that what we have is H of UU transpose is greater than alpha greater than H of I by N. And this now, what if I do something like the following? So if I take H minus sigma I, right, times UU transpose, forget this. So what happens to this? This is nothing but H of UU transpose minus alpha times, sorry, sigma times In comma UU transpose, and this is H of UU transpose minus sigma into norm of U square. With some manipulation, you can show that these two things are equal, and we know that U is actually on the surface of the ball. Therefore, norm of U is actually equals to 1. This is nothing but H of UU transpose minus sigma, right? And what happens to the right hand side? H minus sigma in by n. This is also again equals to H of in by n minus sigma times in comma in by n, and this is nothing but sigma, right? So you can see that, I mean, taking like subtracting this sigma in from H does not change the inequality. So here also you get a minus sigma, here also you get a minus sigma. So things just get like translated by a scalar. So then again, with W log, we can assume trace of H is equals to 0. Why? Because whatever, if H is a non-zero trace, then you can basically replace H with H minus trace of H times In, right? So here for the value of sigma, you can set it to trace of H if H is non-zero. And with this H, you can still have this guarantee. So therefore, it's fair to it's without loss of generality that trace of H can be assumed to be zero. So therefore, now we will see that how these things will happen. And the idea is that let's look at the ellipsoid which is given by in plus delta h to the power minus half times bn. This is an ellipsoid because, okay, so here the thing to note is that delta greater than 0 is small enough such that in plus delta h is pd. So you can think of it this way, that whatever is the most negative eigenvalue of h, you can set a delta small enough such that delta times that negative eigenvalue still is smaller than 1 in absolute value. So then what you will have is that basically uh, the thing is that like this matrix has eigenvalues 1 plus delta lambda I, where lambda I are eigenvalues of h. So if you take delta small enough, implies 1 plus delta I is greater than 0 for all i's, right? So we will see what choice of delta works, but for now let's assume that we have a choice of delta such that this is positive definite and therefore this is indeed an ellipse. So how much is the volume of this ellipse? Volume is volume of Pn times determinant of this quantity, and determinant of this quantity is actually uh, square root of determinant of In plus delta H. This is just a determinant tool. Like determinant of a to the power n is actually equals to determinant of a whole to the power n. So yeah, but what we can now say further is that we have this inequality, right? We saw this before also. Determinant of a matrix is this is the product of eigenvalues of this matrix. And so whatever is the eigenvalue, let's call them uh, beta i's, and this will be less than equals to summation beta I by n whole to the power 1 to the power n. This is by AMGM. And this thing is nothing but trace of the matrix In by delta H by n. Let me just. So this is the thing that we have. And now we know that trace of this thing is nothing but trace of In, which is n, plus trace of delta H, which is 0. This is n by n power n, which is 1. So therefore, what we have is that 1 by square root determinant of In plus delta H is actually greater than 1, right? Therefore, volume of E greater than, let's just call greater than equals volume of Pn. So this is indeed an ellipsoid of bigger volume. In fact, this inequality is strict because H has at least, so H is a trace zero matrix, right? Trace zero symmetric matrix. So it has at least one positive eigenvalue and one negative eigenvalue. And of course, because h is not equals to 0. Because recall that separating hyperplane theorem says that there's a non-zero separating hyperplane, right? So therefore h is non-zero and its trace is 0. So this implies that the there exists at least one positive and one negative eigenvalue. So these quantities which are beta i's, right, which look something like 1 plus delta times lambda I, where lambda is defined here, right, the eigenvalue of h. So this, so there exists one lambda I which is positive and one lambda I which is negative. Therefore, beta I not equals to beta j. I mean, there exists a ij pair such that beta I not equals to beta j, and we know that in ANGM inequality, the inequality is strict when the elements are dissimilar, right? Not equal. So therefore, this holds with strict inequality, and therefore we have found an ellipsoid which has bigger volume than the volume of Bn, right? So our goal was to show that like the maximum volume ellipsoid of K has, so Bn was given as the maximum volume ellipsoid of K, and now we have an ellipsoid which has a bigger volume than Bn. But the only thing that is remains to be shown is that we need to show that the ellipsoid belongs to, like the ellipsoid is a subset of contained in K. And to show that, it's rather a little more algebraic manipulation. So first, we will look at this. So let's look at this set called phi, which is equals to x belongs to Sn minus 1, such that mean of y belongs to delta k intersection delta Pn x minus y is greater than equals alpha y 2 times h operator. So let's see what this is saying. It's saying that look at all the contact points, right, that are there, and on the sphere. So basically, I have the convex body here. I have the Bn. These are the contact points, right? And I want to look at all the points x belongs to Sn minus 1. So points on the uh, surface, like on the hypersphere, that are far away from these contact points. So from all these contact points, it should be far enough. Far enough meaning that it should be at least, the distance should be at least this much. And therefore, we will end up picking something like here. Maybe this arc satisfies. Maybe here there's a small arc that satisfies. There are paths like this that will be included in the set phi, these red parts. So the idea is to first look at these points. And what we will say is that if you extend these points, right, through this red set, and somewhere they will hit the convex set, right? So we look at this point and we will say that this point is outside our ellipsoid. And we will do this for all the red patches. We will keep taking points like this that hit outside, and we will say that this point is outside our ellipsoid E, and we will do this for the set phi first, and then the points that are nearby U, like so call this U, points that are nearby to this contact point. In some sense, those points will not lie inside this the ellipsoid E. And why is that? Because first note that this ellipsoid, which is given by in plus delta h, right? So let's look at what happens if we put, like, if we look at the point U, is it within the inside the ellipsoid or not, right? So for it to be inside, so there the ellipsoid is given by this thing times Bn, right? So if there exists a point such that In plus delta H power minus half times V equals to U, where U is the uh, contact point, right? Suppose this happens, so let's see if V lies in Bn or not. If V lies in Bn, then we know that U is inside, right? U is actually on the ellipsoid. But if not, then we will know that it is outside the ellipsoid. So what this means that V is In plus delta H power half into U. So what happens to the norm of U? Look at norm of U square actually. So this is U transpose In plus delta H into U. And this is basically norm of U square plus delta into H of U transpose, right? Basically, we wrote U transpose H U is equals to H of inner product of H and U transpose. So here we know that U actually lies on the sphere, right? So therefore U's norm is 1 plus delta times this H, and this quantity is greater than alpha, right? So in fact, I should write here this H of U transpose greater than. This is by our assumption here. So what we saw by the separating hyperplane theorem, right? By this we have H of U transpose greater than alpha. And since our matrix here, this thing, we had a trace zero matrix, right? This trace zero matrix actually implies that H of In by N is equals to 0, right? Because this quantity is nothing but equals to trace of H by N, which is 0. And therefore, if you replace this here now, this you set it equals to 0. So that means that your alpha is strictly greater than 0. So therefore, this quantity is strictly greater than 1 by the virtue that alpha is strictly greater than 0. So therefore, our V is strictly greater than 1, which means V does not belong to Bn. So basically, you cannot find a V in the set Bn such that this equality holds, right? So essentially this says that U is outside this ellipsoid. Therefore, U does not actually, U is outside. And so as I was saying that if U is outside this ellipsoid, then what will happen is that the points that are nearby will also be outside the ellipsoid, because ellipsoid in some sense is a continuous sort of a thing, and if at this point it's outside, it cannot have that all the points around it are also are inside, right? They also have to be outside. So we cannot have the nearby points lying inside, and we will show that the far points are also outside. So therefore that will conclude the proof that this whole ellipsoid is contained inside this set, and therefore we will arrive at our desired contradiction. So to do that, we first define this set V here, right? And for the elements of V, let's look what happens. So pick V belongs to V, right? me just copy the definition of V here. This is our V. So what we have, let's pick a V in V, right? And we know that this V in V, right? This is since so this is actually on the surface of the sphere, right? And therefore this V, and since Bn is contained in K, that means that V is inside K. Inside meaning is the interior of K. And so there exists some T greater than 1 such that T times V lies on the boundary of K, right? It's basically this idea that if you extend this, so if you extend this point, you have to extend it by a factor greater than 1 to get to a point on the surface. Fine. So we have this. And now let's uh, look at what happens if let's define this quantity called lambda, which is minimum of my x belongs to V, h of xx transpose, right? So I'm looking at what happens to the inner product of this h and xx transpose for all x in the set V. And we know that h has a negative eigenvalue, right? So h as a negative eigenvalue means that if so there exists basically a vector, the negative eigenvalue can be the minimum eigenvalue is also defined this way, right? Mean of y belongs to Sn minus 1 y transpose hy, right? This is the lambda mean, the minimum eigenvalue, and this is known to be negative. So there exists some w belongs to Rn such that W transpose Hy, sorry, HW is strictly less than 0. I mean, in particular, you can in fact choose W to be the minimum eigenvector, like eigenvector corresponding to the minimum eigenvalue, and that works. So it's fine. So this we don't make any assumption on that. We just say that there exists some W, right? And if this happens, then what we have is that 0 less than W transpose HW, and this can be written as basically H of W transpose, right? And this now you can write as H of UU transpose. I'll tell what U is. H of U, so H comma W minus U into U transpose plus H comma U into W minus U transpose, right? I mean, this is just an algebraic manipulation. You can see that this UU transpose and H, this will cancel out with this. You will have WU transpose, and here U and W transpose. So those are the same things because H is symmetric. So therefore AUW here and WU here will cancel out. We will be left with uh, yeah, we will be left with mistake here. This should be, yeah, this should be W. So we'll be left with W transpose, which is the same what we started with. And now the interesting thing to note here is that let's choose U to be lying in the contact point set. So therefore, this first quantity, we know this is greater than alpha. And second two quantities, we know that they are greater than 2 times h of times w minus u times norm of u, right? And this basically just means that this is just a Cauchy-Schwarz and using the definition of the operator known. And now, if you have your w, basically this means that the norm of w minus u is strictly less than alpha by 2 times norm of h. So note that this is equals to 1. So this happens, right? And what does this mean? This means that my w must be inside the set v, right? So look at v's definition and look at here. So here we have that w is less than u, and this inequality holds for all u, right? Here we did not specify what u are we picking. We just have that u is in the contact point set. So this holds for all u, and therefore w, sorry, the inequality should be reversed. So basically this means that my w is in the set phi, right? So from here we conclude that w belongs to. So w belongs to v basically means that there is at least one element in v for which h w transpose. So basically this implies there exists at least one element in v such that h of v transpose is strictly less than 0. So this basically means that our lambda mean that we defined here, right? Sorry, not lambda mean, lambda that we defined here, which is the minimum over all x in v, h of xx transpose, this is less than 0. So that is what we have. This implies lambda strictly less than 0. And if lambda is strictly less than 0, then what happens to the norm of basically dv times dv transpose in plus delta h into dv, right? Where dv is belongs to delta k, right? T greater than 1. So what happens to this? Basically, we want to now check whether dv lies inside the ellipsoid or not. Basically, this is exactly how we checked whether u was lying inside the ellipsoid or not, right? So we will check whether the norm of the quantity here, right? If this is less than equals to 1, then we know that it's inside the ellipsoid. If it's not, then it's outside, right? That's what we will check here. So we will check whether this is less than 1 or greater than 1. So what we have here is, this is nothing but t square times v iv. So this is norm of v square plus delta h v transpose, right? And now this is basically t square times 1 plus delta into some quantity, right? We don't know what this quantity is, but what we can do is we can lower bound this. So we know that h of VV transpose is greater than lambda for all V belongs to V, right? So we can say that this is greater than equals to T square plus 1 plus delta lambda. And now we can again use another lower bound on T. So note that define this quantity, right? D, which is the minimum of it's the minimum of T, right? Such that TV belongs to delta K, where V belongs to V. So it's basically the minimum of the scaling parameter you need, right, to get this quantity uh, to be large enough to reach the surface of the uh, thing, surface of the convex body. And if you now pick uh, our delta to be strictly less than 1 minus d square by absolute value of lambda, then this quantity you can show that it comes out to be strictly greater than 1. So this means that the point TV is outside E. This is the first part, and it shows that in our diagram, these points, right? Points like this points here, whatever, wherever you can extend this set, red set to be all of the segment on the boundary, all of the segments on the boundary will actually end up having being outside the set, the ellipsoid that we have found so far. And therefore, all that remains to be shown is the fact that the other points which are closer to you, those are also outside the ellipsoid. And that is somewhat easy to show because we already have the guarantee that u is outside the ellipsoid. And now we have to just look at points which are close to you. So now we are concerned about the points which are in Sn minus 1 into V. And these are points for which there exists some u belongs to the contact point set such that so V minus u is strictly less than alpha by 2 times norm of H. Right. So let's look at what happens to H of u transpose minus H of VV transpose in absolute value. So this we can basically again write this as H of, let's just write it this way, VV transpose of this thing. So basically you can see that here VV transpose survives, VU transpose and UV transpose, they will cancel out. So here you will have UU transpose left, here you will have VV transpose left. So this is now upper bounded with like triangle inequality. So H of V into V minus U transpose And again, we apply the operator norm and the Cauchy-Schwarz inequalities. So we will have this is h of plus norm of v times norm of v minus u plus h norm operator norm times norm of u times norm of u minus. And this is equals to 1, this is equals to 1, this is less than alpha by 2 norm of h of v. This is also similarly strictly less than alpha by 2 times h norm. And so therefore this whole quantity is actually less than alpha, right? So what we have shown is that this quantity is less than alpha, and we'll see how this will help us. So now let's look at what about the point t times v again. So t times v belongs to delta k, and v is from the set Sn minus 1 minus v, right? And t is a scaling factor. So again, t is greater than 1. So let's look at dv transpose in plus delta h into dv. Again, by simplifying, we'll end up getting t square into 1 plus delta of h vv transpose, right? And this, now we have a nice lower bound on this. So by the fact that HUU transpose and HVV transpose, these two quantities are separated by at most alpha. So we have H of VV transpose is at least H of UU transpose minus alpha, right? And H of UU transpose again is, yeah, this is strictly greater than alpha. So this quantity here, this is strictly greater than 0, right? So what we have is this is greater than t square into 1 plus delta times h of UU transpose minus alpha, and this is strictly greater than 1 because this quantity is strictly greater than 0, this is strictly greater than 0, this is greater, this is 1, and t is also strictly greater than 1. So therefore dv also lies outside. So thus what we have ended up showing is that all the points on the boundary of the convex body are actually outside the ellipsoid. So all points delta k are outside. Therefore, E is totally contained inside the set K, and volume of E is greater than volume of Bn. This is contradiction because we started with the assumption that Bn is the maximum volume ellipsoid for this K. Hence, what we conclude is that In by n indeed belongs to the convex hull of UU transpose equals to delta B. So specifically, this means that there exists U1 to UM belongs to delta K intersection delta Bn, and U1 C2 Cm greater than equals to 0, such that summation Ci UI transpose equals to In. And here the fun thing to note is that by this thing, right, we now know that by Carathéodory's theorem, that here the M does not have to be too large. Essentially, you need M to be as large as the dimensionality of this vectors, right? So when I said first that you write this as long vectors and take the convex hull. So those long vectors actually have n square entries, but in truth, they have actually n into n plus 1 by 2 distinct entries. Like, because it's a symmetric matrix, and when you write it out, so you will have the ij equals to ji, so you can throw away a lot of redundancies, and what you will be left with that there are actually n into n plus 1 by 2 uh, uh, actual dimension, right? So m equals to this much suffices. Sorry, this much plus 1 by Theodoric's theorem. This completes the proof of Chom's theorem, and this we'll see a nice application of this Chom's theorem in optimal design. And this is a very beautiful theorem about convex bodies in general. And this has been used extensively in multiple areas. In fact, in ellipsoid method for solving LPs, in approximating volume of convex bodies, in sampling from convex bodies efficiently. So this is like one of the very nice core theorems of convex geometry. And yeah, so yeah, with this, I'll end this video here. And in the next video, we'll discuss optimal design.